Thanks for joining us today. It's a pleasure to introduce our distinguished speaker, Dr. Susan Cormier. She's a senior scientist with over 35 years of experience at the US EPA. And so Dr. Cormier's career has spanned the full spectrum of environmental assessment, from developing national biological monitoring methods to pioneering ecological causal analysis frameworks like the EPA's CADDIS system. Dr. Cormier received her bachelor's from University of New Hampshire, her master's from South Florida, and her PhD from Clark University. And she's, before the EPA, worked at Vassar College and the University of Louisville. And so this morning she's going to be talking about and introducing the EPA Freshwater Explorer 2.0. And I think with that, people have probably heard me speak too much already, so I'll hand it right over to Susan.
Okay, thanks everyone for joining us this morning on this quick invite. And the invite is because I will be leaving the agency the end of the week. So this is my, I guess what it is, some kind of tour, last tour that I make. Anyways, other speakers, as you can see, I have Sean Timmons is on the line, and he'll be one of the folks taking over for some of the work that I do. Chris Wharton is with Tetra Tech, and he's responsible for the actual mapping tool that you're going to see today. And there are other folks as well, but for today's talk, those are our authors. All right, so there we go. So anyways, this is the landing page for the Freshwater Explorer. Here's the link, and all of these slides are in the chat. So you can, find the link very easily. But to be honest, the way I always do it, I just go to Google and I go US EPA Freshwater Explorer, and it pops right up and I'm in. So that's one way to go, or you can go to the landing page. The beauty of the landing page is that there is this quick guide. And a lot of the slides that I'm showing today and some others help you through, the real basic things of kind of becoming familiar with the tool. And then this is another way to access the Freshwater Explorer. So obviously, if this is Freshwater Explorer 2, there must have been a Freshwater Explorer 1. And so now this is a new system, and it's because the first one was a story map. This one is actually on an Esri platform that allows, all the capabilities you would have on that platform. But we've done it in a way that you can start with it with simple things and then move on to more difficult things as you become more and more familiar with it. So if you're familiar with Google Maps or any other of the map programs, Bing, Outlook, whatever, you can do this. So it has a lot of capabilities, but easy to use. The other thing that we did was we developed, so right now when states or anybody gets money from EPA, they need to provide data. They provide data back to EPA, and they house it in a warehouse called the Water Quality Portal. And the problem is their data may be gorgeous, and I know this for a fact. It's gorgeous if I get it directly from them. But if I download it from the Water Quality Portal, there's all kinds of mistakes. Things are put in wrong columns, units are wrong, all kinds of things go wrong. And so there's now a system called CADDIS, which does a cleanup. And then we have added additional cleanups to remove things like negative numbers, which are silly, and other things like that, so that you get back to almost as good as if you asked the states or somebody else for that data. So that gives people access to lots and lots of data, millions, and I'm not kidding, millions of data points that have been added and saved in the Water Quality Portal. And what this tool does, it allows you to do all kinds of things. The other thing we did was we started out with just conductivity as our first measurement that we put in because of the kind of work that we needed to do. But now we're adding all these others. There are now, I think, 11 or 12 of them, and we will be hopefully adding more in the future. So what do you get? So when you open it up, what you see is the United States, and even though I'm showing only the lower 48, there are data for Alaska, Puerto Rico, Hawaii, etc. So the first thing is the measured data. So this is the data that we pull out of the Water Quality Portal, and we do a little bit of cleanup. And what you see it as little dots. And each one of these dots represents a sampling station, and the color is telling you something about the concentration at that site. And this is an example of total phosphorus. The second thing we did was add background estimates, and we have two flavors of this, if you will. The first one is for all of the ones that we have identified the 25th centile of the medians of the data for an ecoregion, a level 3 ecoregion. And you can see an example here for alkalinity. So lower alkalinity, as in some areas, and higher alkalinity in others. Then the other thing that we did for conductivity, and we haven't done this for all the others, and it would be difficult for some of them, but for conductivity, it worked really well. We have a model that predicts the background conductivity for stream segments. So every little stream segment, and of which there are thousands of them, maybe there's a million even, you can click on those and see what is the predicted background. And this thing is really accurate. It's within 100 microsiemens and predicting what the natural background would be. This is not predicting what it is if everything's been added. You would use a different model for that. Each one of these data layers, there's a metadata page. And if you go up into this little thing that people call it a hamburger, you click on that menu and you can select the metadata for every one of those different data layers. And it tells you how we cleaned it up and how we have adjusted for different units that have been added by the different entities that added their data to the water quality portal. So these are the coverages of the data layers that are available. And so that was where we started. And I think for this group, you can see that there's a lot of them that include the various ions, which is particularly useful. So, what are we going to do next? I won't be here, but hopefully what will happen next is additional ones will be added. There's been a real interest in adding biological data, which is available in the portal, and adding those, as well as things like pathogens, or other metals, other variables. But I'll tell you, it's just like anything else. What we added or are in the process of adding is where we were able to get funding. And so we're adding PFOS and PFOA at this time. And just to give you a taste of what that looks like, this is draft. Please don't share this. It's not ready for sharing, but I'm sharing it with you just to give you a taste of it. This is a map that was created by Sean. And you can see the different each one of these are the different types of media, and each one of these are a state. And I don't know why they stick Wisconsin up there, but he's up there. It should be Minnesota. It's got the little bump. And here you can see Puerto Rico. No data for Alaska and for Hawaii. However, this is only the data in the water quality portal. We know that there's additional data in the NARS data. This is data that EPA collects in conjunction with states, and we're going to add that as well. So this is a preliminary view. Okay, how do you use the Explorer? Like I said, it's just like Google Maps. A lot of the things you see, you're used to. On one side are the data layers that you can choose and add to your map. And on the other side are the tools for doing things with it. And then, of course, there's the usual things to zoom in and out of the map, return to your original area, search for a place, or let's say you're down deep in some place that you're not familiar with, like some little corner of Colorado, and you go like, where am I now? You just click on here and it'll show you a little inset of where you are. So I want to go a little bit into the tools now. So here you can see those icons popped up, and what they call this in the mappy world, they call these widgets. And so here you can see the one, you just type this in and you can get an address. This changes your background or your base map, measure it. This is to choose data you want to pull out. This tells you what data layers you have loaded onto your map currently. This is if you want to bring in data that we haven't curated, but there are over, how many are there? There's over 10,000 of them that are available on the Geo platform that you can pull in. And this is for analysis. This one you can't really use unless you have an Esri account. However, you can export the data and then you can do analysis in any other tools that you have, even in Lotus Notes. So in addition to the tools that are over on this right-hand side, when you pick a particular variable, let's say you pick conductivity and you want to look at rivers, you can choose those, first of all. And also note that if you choose these things, if you see one of these little arrows, that means there's more information below. And you just click on it and it shows you them. And then you can choose your features, rivers in this case, but lakes, wells, whatever. And then this thing is when you have multiple layers, sometimes they're getting on top of one another. You probably have done this in PowerPoint where you send it to the back, you send it forward. You just take this thing and you drag it up and you can put one thing on top of the other. And then these little dots always mean there's more information. And if you click on that one, what you can see is it pulls down a little menu, and there's all kinds of things here. But one of my favorite is to filter. And so for instance, say you just want to look at USGS data, you can just choose just to use USGS data or your own data or somebody's data or a state or a particular state. And then the other one is export, because you undoubtedly want to pull data out. Now, I don't recommend pulling out everything at once because literally it's millions and millions of data points. So you want to select pieces and then export what you're interested in. All right, so let's go ahead and just do a canned, if you will, example so that you can see how this is done. Here you can see I've typed in Denver. I've clicked on the little magnifying glass and you can see Denver. And then I would pick from amongst these, do I want the airport? No, I just want Denver. And so I would click on that and then I can change my base map as well. And the reason I do this is because with satellite imagery, it's just too busy to initially look at that data. So I like to always pick something really plain. And then later I go back to these other ones as I need them. So if we click on that one, this is what pops up. And here you can see under the measured water quality tab, I have selected conductivity, and it's already popped up on the map. And what you can see is that there are different colors. The higher colors are for our higher conductivity, and the warmer colors are lower conductivity. And then I can click on the estimated background. And here I'm predicting the one that is that high resolution one, predicted background conductivity. And you can see now the streams are also color coded. So this stream would be a higher conductivity, say, than this blue one or purple one. If you click on the little menu on the side, it shows you the legend. So you can see that this is a very low conductivity and these are higher conductivity sites. And the beauty of having the background conductivity on the stream segment is that you can kind of look at the measured conductivity versus what is the background. So for instance, on this one, you can see that the natural background conductivity is very low on this stream going into where the university is. And you can see that the measured conductivity is the same color. So that means that there's no salts really being added. This is about as natural as you get. In contrast, if you go over here, you can see this stream, its natural conductivity, probably a little bit more arid, is expected to be a little bit higher, more in the 200 range. But you can see that the conductivity levels are much higher, the red, many times higher. And so salts have been added into the stream here. And then it's always interesting to see places where there's a transition. So you can see here where it's going from lower conductivity to bingo really fast to high conductivity. So obviously there's some kind of a point source there. So that's sort of how you can get that first initial visualization, or if you are telling a story, to be able to share it like I am today. So one of the things that you can do is also you can select a site. If you select a site or a stream segment, it turns this turquoise color. And what ends up happening is a menu comes popping up, and you can see the information that's shared. And so you can see the median, I've blown it up here so you can see it, is at this site is over 1,000, and the natural background is supposed to be about 75. And here you can see it again. Here's that transition zone between the low conductivity and the high conductivity. And of course, when you see something like this, you know there's something there. So you then might want to switch your background. And here you can see I've switched it to the satellite imagery. And I've also changed to say, well, what about another parameter? Are we seeing the same thing with other things? Here you can see total phosphorus, and you can see low total phosphorus. And then again, there's a transition right there. It's even closer where this measurement was taken. So something right there. So you could probably go and find the darn pipe. And then, so then the question is, well, what is that? Well, there's a lot of ways to figure that out. The fastest way I did it was simply just to go to Google Maps, but you can do it by looking at attains, for example, and you can see it's a beer manufacturing location or bottling plant. All right, so then you go, well, do these guys have a permit or what? You know, so you can go in to this little icon over here where you can add data. So there are 10,000 different data layers that you can add, and you just click on that. And then this thing pops up. I don't know why you have to click on it, but you do. And you click on it. And then this one will come up. And I typed in ArcGIS Online, or I chose ArcGIS Online. You have a couple of choices here. And then, so you just click on it. And then I typed in attains. And these came up. And so then you have to pick one of these. I'm just going to pick the first one because I know it's the right one. But you can also check anytime you see an I, there's more information, and it will bring you to the metadata and information about this particular data layer. So now we're going to choose that one, and then we're going to hit done. And what's going to happen is now going to pull this in from the Geo platform and add it to the map. And here you can see the lines have been added from attains, and all the red lines are where there is an impairment, and these are unimpaired based on what the state of Colorado has put in. And then when you click on a stream segment or whatever piece of information you're looking for, if it's a different kind of tool that you've pulled in, then it will tell you what are some other information. And here you can see I've blown it up a little, that they have identified these causes as being particularly problematic. So even though phosphorus was pretty high and conductivity was high, the state has identified these as being particularly problematic and needing attention. So then the next thing is, well, maybe you want to pull out some data. So there's a number of different tools. You click on this little guy here with the little arrow. It says to export, and these things will pop up. And what you do is you have to pick what you want to choose. In this case, I picked a lasso tool, which allows you to just drag a little thing around the data you're interested in. And then you get another little, you click on this and you get another couple of little pop-ups, and you can choose to export the data. This pops up, and how do you want to export it? In this case, I'm just exporting it as a flat file into my Excel. So here's from my computer a screenshot. I exported it. I did organize it so that I would go from upstream to downstream using the lat long. And then I just, did a baby map for you to see how easy it is. You can start to see here's upstream, and then you get to this point and conductivity goes up. But you can do a lot more sophisticated things, obviously. All right. So here are all the kinds of applications that are really easy to use. You can do data extraction, characterize background, and it's really useful for pattern recognition. And now I'm going to do some examples. And this is so that it's kind of gives you the feel of what this is really like. So, and I know I'm going super fast, but it's because I've added some extra ones for you because I know of your interest in produced waters. So the first one is assessing criterion suitability in Wyoming, and this is for chloride criteria. The next one is for assessing the potential downstream effects of mining in Minnesota. And this is for a mine site that was proposed in northern Minnesota, in which they would be one of the things that was being released from the mine site was minerals, including salts. Then the next one is nutrient and conductivity criteria development. That was done by the Grand Portage Band of the Lake Superior Chippewa. Then the last one is not so related to the work that you do, but I thought you might be curious of how the analysis was done. And this was a risk assessment for 6-ppd quinone effects on brook trout in Pennsylvania. And we'll get into the details as we go along. So here's the first one. So what you can see here is a little piece of Wyoming. This is the Bitter Creek watershed. It empties into the Green River that goes down to the Colorado. And the question that was brought to me by Region 8 in Colorado, and I'm sorry, and also Wyoming, was that they were thinking about changing their chloride criteria. They had it set at the level that was recommended just, nationwide by the EPA. And they just were wondering whether or not, they have a lot of arid area. They have a lot of places where there's just, saltier in general, and whether or not the criteria was appropriate. And they felt that they might want to change it. So they asked me to look at it and do an assessment for them. And what you can see here is the background conductivity map. And you can see that this is area that would be expected to be somewhat higher, naturally higher. And these green areas are places, these streams are expected to be, not very high conductivity. The dots are for chloride concentration, because that's what they were interested in. I didn't have a map for chloride, but conductivity was a good first estimate, because the relationship between chloride and conductivity in this area is almost 1-to-1. So what you can see here is that there are plenty of places that have low chloride, and you do have some with high chloride. And then if you look at, for instance, Bitter Creek itself, you can see from upstream to downstream that the chloride levels are low and less than the chronic criteria for chloride. And then they start to creep up. And finally, in this section of the river, there are places where they are exceeding the acute levels. And in this other fairly large stream down here, Salt Wells Creek, you can see that almost all of them are low, less than the chronic criteria. And so, what that's telling us is that, indeed there may be places where it would be appropriate to have site-specific criteria, but if you simply changed everything to accommodate these high places, you would then be potentially not protecting all of these streams that are just so important because they're providing the dilution in the fresh water. And these areas in here, you can see there's no sampling going on, and that's because they're just flowing during storms. And so as a result of the assessment, the outcome was that the state did not pursue the option to raise their chloride standards. And of course, this wasn't the only data that was used in this assessment. It was, I don't know, 100, 200-page report. But it's pretty much the thing that convinced people that this was the way to go. All right, here's the next one. The question was, there was a mining company that wants to build a mine here in the Superior National Forest. And here you can see it. And there was an abandoned mine here that is unfortunately a lot of acid mine drainage coming out of it. But they wanted to put this one here, and they were making some proposals about how they were going to do things and whether or not what they wanted to do was if they added minerals here, what would happen down here? Now, the mining company wasn't so concerned about what was happening down here, but there was a tribe here, the Fond du Lac tribe, who have water quality criteria on this river. This is the St. Louis River. And they were concerned that by adding salts here, that this would raise the conductivity here and exceed their water quality standards. And the distance here is pretty far, So it really was unclear whether that was really going to be an issue or not. So, there was all the salts coming in from the Mesabi mining area and also from this highly contaminated area. But then there was all this nice, really low conductivity, low salt area that was doing, a pretty nice job of dilution. So they asked me to look at it. So this is how I started, by first looking at the map and saying, okay, who knows? Let's see what we should figure out. So the dark spots are the St. Louis River right here. And here is the criteria for the Fond du Lac tribe. And what you can see is that in the upstream portions right here, before the mine waste would come in, it's very low conductivity. So is all of this area, very low conductivity. And then as you can see, when you get right here, when the drainage would be coming in from here, even though it's not built yet, it's coming from this one primarily. There's a lot of salts coming in and low pH, and the conductivity makes the St. Louis pop up. And then you can see roughly, how that is changing, and it's getting lower as it gets down to where the reservation is. And so here you can see all the major streams popping in here. And the bottom line was that unfortunately for the mining company, the conductivity levels occasionally were exceeding in this area already. And that by they were going to add an awful lot of salts up here. And when I did the model, it would have raised it up so that it was exceeding quite frequently. And so as a result, the Army Corps of Engineers didn't approve the proposal in its current form. And it's likely that the mining company is going to, revise, and there's probably ways they could do it. It's a little tricky, and this is a very sensitive area through here as well. But, if they wanted to do it right, they probably could do it. So here's another one from Minnesota. This is the Grand Portage Reservation in the very tippity tip of Minnesota, and here's Lake Superior. And what you can see here is they wanted to have water quality criteria and establish standards, and they had been doing it for like 20 years trying to get this done. And so I was asked by Region 5, and I worked with Margaret Watkins, who's awesome, from the Grand Portage Reservation. And first we started out with a map, and you can see that there are some places where phosphorus is high, and then there's plenty of places where it's also low. And the issue was that there was some that were high, like this wastewater treatment plant, but it's dumping into Lake Superior. And the question is for this whole other area on the reservation. And part of the problem was the levels that they thought are appropriate for setting their phosphorus criteria were higher than what was being recommended for some places in the rest of Minnesota. And so we started just looking at pairs. So here's in the lake and here's in the stream. And that's what you can see is that this is the lake, and it's low conductivity. As you go downstream, beaver, beaver, beaver dam, beaver, beaver, and it keeps on going, more beaver dam. And then finally, it's a little bit higher in the river down here. Not outrageous, but it is higher. And then if we look at Mount Maud, you can see here, it's higher in the wetland and lower in the open body of water here. And this is really, again, the same, what we found in this analysis was that the lakes that are on the reservation are more shallow and smaller than in the rest of Minnesota. And that's why there was a difference between the phosphorus levels. We also did lots of other analysis, and I can tell you there's probably more beavers than people up here. There hasn't hardly any logging that's been done in the last 100 years. There's no other real activity. There's a few roads and hardly anybody living here. They're all here on the coast. And so these natural areas, it was just naturally high. And so we did a cutesy little model, as you can see here, with little PowerPoint grabby pieces of icons. And what it is that there are these huge peat deposits, and the water is flowing down into the groundwater and into these lakes and into the streams, and it's dragging with it a lot of dissolved organic matter, and the water is also low pH. And then what happens is the muskgrass, which is covered with calcium carbonate, neutralizes it. So these waters are actually at neutral pH after coming in, even though at low pH. And then what happens is the beavers are damming up everything as well. So you've got all this nutrients coming in, and the beavers are damming up places as well. And all the wetlands are also, maintaining all that nutrients. And the moose are coming in, and bioturbation is going on, and they're resuspending it. So the nutrient levels are just naturally high. There is some coming in from atmospheric deposition as well. And of course, ducks are coming in here and other waterfowl, and also bring in nutrients. But what's coming in from atmospheric deposition, is probably, higher due to anthropogenic changes. And there's been quite a few things on climate change to suggest that that's also affecting it. Yep, there's the beaver. But I want to emphasize that there's lots of other evidence that gets used in these things. And here's one of the pieces of evidence that was really key. What you can see here is that cores in some of the lakes were taken, and from 1760 until current times, total phosphorus has not changed. It's actually decreased a little bit. So, obviously these are natural conditions. And what was interesting about what the Grand Portage Band wanted to do is they wanted to maintain things in its natural state. They're not looking for assimilative capacity or the ability to add nutrients and see how much they could add and still maintain good conditions. They want to keep it natural. So the way they decided to do that is to use the median levels of natural conditions in order to establish it, and then use the assessment that I did with them to show that conditions were indeed natural and not anthropogenically altered. So as a result, yay, Grand Portage Tribal Council approved their water quality standards, as did Region 5 and Office of Water. And after 20 years, they finally got criteria for nutrients. And we also did it for conductivity. And they did it two ways. And they didn't do it. Now, what happens is a state or a tribe, they're the ones who set the criteria. It's not EPA. They make recommendations, but it's the states, tribes that set their standards. And so in cases where they had this particular species of fish, this is a brook trout. It's a coaster brook trout, goes out into Lake Superior, it gets nice and big and fat, and then comes back into the streams. So in those streams and lakes in which there were coaster brook trout, they set their criteria based on the sensitivity of conductivity to this fish species. And the way this was done is we looked at lots of places in Minnesota in which the brook trout occurred and looked at the conductivity. And what we saw, and then we estimated with this GAM plot, the probability of observing the coastal brook trout or the brook trout. And you can see that as conductivity increases, the probability of observing brook trout decreases, and some of these are even stocked. And at this point, only 5% of the brook trout are observed. And at this point, there's a 50% probability that you would not see the brook trout. And so they decided to set it at this very low level for those streams that had brook trout. Mind you, even though this is a super low number, the streams are super low salt content. They're down in the 30, 40 range for conductivity. So just so you have a sense of if this is a good way to go, this is an example from West Virginia that Greg Pond provided me. And essentially what he did was I had provided him with the point at which a benthic invertebrate in a stream in West Virginia would not be seen, or only 5% of the time it might be seen in a stream. And then took each one of those values and put it on a plot. So increasing conductivity and just the proportion of sites. And what you can see in this particular stream, which has very low conductivity, there's lots of different benthic invertebrates, and at the point which, and conductivity is great. In this one, which is just the same sort of a stream right next door to it, but it has very high conductivity levels because of mountaintop mining, I believe, in this case. You can see there's very few species of benthic invertebrates. And the ones that are sensitive, that are extirpated, below 1726 are not present in the stream. So it's a pretty good, indicator, a pretty good tool for trying to figure out criteria. So what the Grand Portage folks did was we used a similar method. So here you can see we had data for 24 different ecoregions around the country, and we estimated the point at which each species would be extirpated. And here you can see it's happy here, Dronella, this mayfly, and it's not happy, just slightly over 100. And we did this for 100 to 200 benthic invertebrates, depending on the ecoregion. And you can see here then that if we put, that's these particular ones, this value, conductivity. So this would be Dronella. It gets lost. And then the next one is extirpated, next one, next one, next one, next one. And then finally you get to the 5th centile. So at this point, 5% of the benthic invertebrates in this particular ecoregion are likely to be extirpated at conductivities greater than 338. And these are all the other 139 genera of benthic invertebrate XC95 values. So, like I said, we looked at 24 different ecoregions and made plots like that. And we also estimated roughly what was the background in that data set at the 25th centile. And you can see some places had higher conductivity than others. Fortunately, we didn't have any up in this region, which tends to be really high, or down here, which is very high. But we were able to model at least this much. So here are each of those ecoregions, and this would represent the benthic invertebrates, and here's the point at which 5% would be lost. And here would be one at an ecoregion with higher conductivity naturally in its background. So then we took those 25th centiles of the background here on the x-axis, and on the y-axis, what was the point at which we would lose 5% of the species. And so here you can see the one for North Carolina, it's very low. And then for other places, it can be quite high. Now, with this regression line, you can just put in the background for an unknown place, and let's say it's about 100. Well, this one, my little line just didn't get moved, got bumped. But at any rate, it will, if you put it in, you come up to the line and you come over, they will give you the background. It'll give you the point at which you would lose 5% of your species in that particular place. And that's what the tribe did. For every one of their water bodies, they estimated it based on the natural background because that's what they were trying to protect. All right, last example. So this is coho salmon. And so what happened was in the 1940s and so because of the World War II, there was a lot of problems with the tires rotting away and they weren't ready for the next war. And so there was a real effort to try to find a way to fix that. But unfortunately, as there was something going into the streams and it was causing coho to die. And this was observed in the 80s, and it took them forever to figure out what was the cause of these fish. What was essentially happening was they had cleaned up Seattle's streams and made it so fish passage was possible, and the fish were going upstream during spawning, and then they would just die, full of eggs, and never even got a chance to spawn. They die within hours. And it was due to what we found out in 2022, which is only recently, was that it was due to 6-ppd quinone. So this is what a tire looks like. For you old folks, you might remember having bicycle tires that would also crack and everything else. And that's because they didn't have 6-ppd in them. Now almost all tires have 6-ppd. And what it does is the 6-ppd is sitting in the tire, and on the surface of the tire, it's exposed to ozone and high temperatures and oxygen. And what it does is the 6-ppd grabs the oxygen and protects the rubber from being broken down. So it makes the tires, prevents their cracking, makes them last longer, makes it safer on the road. And it's because of this preferential grabbing of the ozone by the 6-ppd to form 6-ppd quinone. And then this sloughs off, and then more 6-ppd comes to the surface, and again, the process just keeps repeating itself. The problem is when it gets onto the road and then it gets washed in, it kills the coho. So what people started to do only in the last couple of years is they said, well, what about everything else? So coho, you can see, has a very low LC50. We're talking nanogram amount will kill them in hours. And the brook trout isn't quite as sensitive. Rainbow trout not as sensitive, but they're still sensitive. The brown trout not sensitive at all. And so I asked the question, I was on an ITRC work group, and I wondered, well, can we just see anything at all? And what you can see here is a map. Whoops. What you can see is a map of the United States, and you can see the areas where either coho, rainbow trout, or brook trout, these 3 sensitive, and there are others, species, the natural range, and this is their introduced range. So you can see it's not just a problem for Seattle, potentially. So I said, okay, let me see what I got for brook trout. So fortunately, Pennsylvania had data set that I had access to I was using for a different reason. They said it's okay to use. And you can see these are the areas in which brook trout are present, and these are places where brook trout were not observed. And anytime you see a straight line, you have to get suspicious that looks like man-made. And so here you can, so what I did was I just grabbed a coverage for the major roads. And you can see here where it's following the road. And so then we can start to look at some additional things. This is just the first look, right? But it tells us, what else could we do? And we can start to pattern our investigation in ways similar to what was done with the coho. So the question is there a source effect relationship between the roads and brook trout? And we would expect not to have one for the tolerant brown trout. And the reason we're doing roads is because nobody has measured any 6 ppd yet in Pennsylvania. And I could only find one spot where there was a measurement in West Virginia and 1 or 2 in Maryland. So there was just no 6 ppd measurements. So I was using roads to see if there was an effect. And what you can see here is we have brook trout and rainbow trout in a bunch of different variables. And I've highlighted the ones that are associated with traffic, impervious surface, road density. And you can see that there's a positive relationship between brook trout, or I should say a negative relationship with brook trout, and things that have to do with roads. And brown trout, yeah, they almost have a positive, slightly positive effect. So then the question becomes, well, is there enough of the stuff to make a difference? We should, if that's true, then we should, as we see more roads, more traffic, we should see a greater effect to the brook trout. So as road-related variables increase, the probability of observing brook trout should decrease. And so just like I showed you those little GAM plots before for the coastal brook trout, we did the same thing with brook trout, but now with these variables instead. And you can see as impervious surface increases, the probability of observing a brook trout decreases. And as road density increases, they go down. And as traffic increases, they go down. Meanwhile, we would expect not to see that with a intolerant or a tolerant species like the brown trout. And here you can see brown trout with impervious surface, road density, and total traffic. Yeah, I don't care. Yeah, pretty much flat. So this was evidence to suggest that we should do something. We ought to look into it. It's not, we don't know for sure because we haven't even measured the 6 ppd. So what could be done is just need to measure 6 ppd quinone in more places and determine if exposures are toxic. We can just put some caged brook trout fingerlings out in a stream. Right now, we're not going to really see things in streams. It was possible because everybody was walking around in Seattle looking. And even in the rain, because that's what happens out in Seattle. Whereas nobody's going to go looking in these streams in Pennsylvania in the middle of a storm, and it's probably not safe. And then also we can deploy collection of stormwater for toxicity testing and also for measuring 6 ppd. So I think these are the next steps. And then it's like, oh no, we don't really want to know that answer. But there are things that can be done. And of course, Seattle and the West Coast are and California are leading the way, in Oregon, because of the coho actually is getting to the point where they're really declining and the population is really going down. So one of the things that can do is, for instance, with the Explorer, is that there are StreamCat data layers that you can pull in. And if you load them up, they show the areas, these red areas are places where that has higher impervious surfaces. And also it provides information for the amount of traffic on the road. And so if you click on a little stream segment, you can see that this one, there's minor road crossing it, and there's a major road within 44 meters. And you can see the amount of traffic on this road. So it helps you to start say, okay, where should we put mitigation? And we're obviously not going to put it over here where it's not a problem. Let's put mitigation where it's likely to be a problem. And that way it will be cost effective. And by the way, there's also work going on what you can do for mitigation for these sorts of things. And it is daunting when you think about the total area, and therefore it really is essential to try to figure out where to make the changes. Because the problem is even though folks are looking for an alternative to 6 ppd, they haven't found it. And even if today all 6 ppd was stopped being put in tires and there was a good substitute. It would take at least 20 years for all the tires that are on the road not to be there anymore. All right, bottom line, little messages I'd like to leave for a take home. Freshwater Explorer is easy to use and you can do whatever you want with it. You know, whatever your question is, you can design it. And you can explore all those 10,000 other data layers in there that are available through the Geo platform and use those. You can also start to be able to use and hopefully the data layers that we have put in that have been curated from the water quality portal for that measured data. In addition, there is a way to clean up that other data layers if we haven't gotten to them yet. So say, for instance, you were interested in lithium. You could go look up data, see what data was available in the water quality portal for lithium, and you could use the cleanup procedure from TADA, as well as our other small tips on how to clean them up, and you could just move forward with it yourself. We also are aware that the cleanup procedure is not the same thing as getting the original data from a tribe or a state or from USGS or EPA. So we know that we can't correct everything. So what we do is we color things gray if we are suspicious. They might be right, but we're suspicious because they're very high or very low or something just looks funny. And we like to hear if there's a notification and let us know, and we will try to work with Office of Water to continuously improve the quality of that data. I want to emphasize it's a great way to start an assessment, but of course you need to, if you're going to do an assessment with this data or any kind of analysis, you're always going to need to think about other things and other ways to do things. And although I will be leaving, I know that Sean and others are always excited about partnering on projects. So this is just a quick acknowledgement. I've mentioned Margaret already. The Pennsylvania data came from these folks. 6PPD information was provided by when I was on the ITRC Council. And Micah Bennett was involved with the nutrient criteria. The trout data came from the Pennsylvania Fish and Boat Commission. And these folks have worked on developing various aspects of the Freshwater Explorer. So as I mentioned, I shall be taking the deferred resignation program option the end of the week. So this is my email if you need to get in touch with me after this week. However, Tammy is staying at EPA and Sean is staying, and Michelle is in Office of Water and she is involved with the water quality portal. And Chris Wharton is always available for hire, but he's also very good about responding to folks if you have a question. I provided an awful lot of information here. So here are links that you might find useful and also references, and a lot of these are available free online. So that's the end of my presentation, and I'm happy to take questions, and I thank you very much for my very long-winded presentation.